Ever since you're a kid, you're taught that addition is simple. 2 plus 3 is 5, and 3 plus 2, well, it's also 5. The order just doesn't matter. But what if I told you that when you start adding up an infinite number of things, that fundamental rule can just completely break? And this is where it gets really, really interesting. This quote right here gets to the heart of the paradox. All the comfortable, reliable rules of math we use every day, they can fall apart when you bring infinity into the picture. I mean, that feels like it should be impossible, right? So this is the big mystery we're going to solve together. How on earth can you take the exact same set of numbers, just shuffle them around and get a totally different final answer? It messes with your brain. Okay, let's dive in and figure this out. Right. To get to the bottom of this, we need to really understand what's going on with this infinite shuffle paradox. So, the main character in this whole story is something called an alternating series. And honestly, it's exactly what it sounds like. The signs just flip back and forth. Positive, negative, on and on forever. The classic example is 1 minus a half plus a third minus a fourth, and so on. These are the series where all the really weird stuff starts to happen. Now hold on, before we can even think about shuffling terms around, we have to know if the series adds up to a real number in the first place. I mean, a lot of infinite series just shoot off to infinity. They don't settle down. So our first step is to figure out how we can tame these wild things. Luckily for us, mathematicians have given us this fantastic tool. It's called the alternating series test, and it's basically our #1 gadget for this whole investigation. It's what lets us know if our series converges, which is just a fancy way of saying it actually settles down and lands on a single specific answer. And the best part? This test is super simple. Seriously, there are just 2 boxes you need to check. First, do the terms themselves get smaller and smaller, eventually heading towards 0? And second, is each new term smaller than the one that came right before it? If you can say yes to both of those things, your series converges. That's it. Simple as that. Okay, so let's use our main example, the alternating harmonic series. Do the terms 1, 1/2, 1/3 get smaller and head to 0? Yep, they sure do. Is each one smaller than the last? Absolutely. So bingo, our series passes the test. We know for a fact it adds up to a real number. But this actually just makes the mystery even deeper. Because here it is. This is the crucial clue that's going to crack this case wide open. See, it turns out that how a series converges makes all the difference in the world. There isn't just one way for an infinite sum to land on a number. There are 2, and they behave in completely different ways. Think about it like this. You have your robust sums. Those are called absolutely convergent. You can shuffle them, rearrange them, do pretty much whatever you want to them, and the final answer does not change. They behave just like the normal addition we're used to. But then you've got these fragile sums, the conditionally convergent ones. Their answer depends entirely on this delicate dance of positive and negative terms canceling each other out. If you change the order, you throw off that whole balance, and everything changes. And this table shows us exactly why our series is one of those fragile ones. Look, we already know the alternating version converges, right? But check out what happens when we take the absolute values, when we make every single term positive. We get 1 plus a half plus a third, the famous harmonic series, and that thing just goes off to infinity. So because the original series converges, but its absolute version doesn't, that's our culprit. It is officially conditionally convergent. Okay, we've got all our clues in place. We know our series converges, but we know it's fragile. It's conditionally convergent. So now it's time for the big reveal. And here it is, the solution to our whole mystery. This magic trick of shuffling an infinite sum to get a totally new answer, it doesn't work on all infinite series. It is a bizarre, incredible, and kind of amazing power that belongs only to these conditionally convergent series. Their fragility is actually their secret power. Let's actually see it in action. So if you add up the alternating harmonic series in its original standard order, the number it settles on is the natural log of 2, which is about 0.693, a very specific, concrete number. Got it? But now for the magic trick. We're going to rearrange the terms. The pattern we're using here is 1 positive term followed by 2 negative terms. So we'll take the 1, but then subtract a half and a quarter. Then we'll take the next positive term, 1/3, and subtract the next 2 negatives, 1/6 and 1/8. We are using all the exact same numbers, just in a new order. And the result? Get this. The new sum is exactly half of the original sum. Half. We use the exact same numbers, but by changing the order, we literally cut the answer in half. That is the infinite shuffle paradox right there. Same ingredients, different recipe, and a completely different result. Wild. So what does all this mean? Well, it means that our intuition, which is built on a world of finite, everyday things, needs a major update when we start playing in infinity's sandbox. The rules are just different here. So let's just quickly recap what we found out. First, yes, the order of an infinite sum can absolutely change its value. Second, this mind-bending behavior only happens with those fragile, conditionally convergent series. The robust, absolutely convergent ones always play by the rules. And the big takeaway from all this? Infinity has its own rulebook, and it is full of incredible surprises. I mean, this whole thing shows us that even something as basic as adding numbers together gets completely transformed by the idea of infinity. So the question I really want to leave you with is this. If something as fundamental as the order of addition can break down, what other rules of math that we take for granted might bend or maybe even shatter when we're faced with the infinite?